Hello and welcome to a special pre-recorded episode of The Naked Scientists, which is being recorded on location here at the Cambridge Science Centre. This month we're exploring the world of robotics, including robots that recognise speech, robots that can move test tubes and samples around in laboratories, and even robots that can conquer other planets. Conquering this planet, though, scientists recently built the world's first robotic tractor. Bet you can't guess what it's called? No? Well, it's a transfarmer. Of course, exploring Mars is something of a priority. We want to find the sunniest spots because the first human colonists are going to be due there in the next 30 years or so, and those first pioneers are predicted to be the world's intellectual elite. The reason being, according to space authority Ali G, it's the well-read planet. Let's meet our team for you this week. From my left, please introduce yourselves and say who you are and what you do.
My name is Blaise Thompson, and I used to be a research fellow at St John's just here in Cambridge until a few months ago when I decided to join a startup company building voice interfaces for computers. So I'm on the speech side of the panel and very interested in how computers can learn to understand language.
You know, as a medical doctor, Blaise, I've actually seen efforts to use computers to transcribe medical recordings in the past, and I've lost count of the numbers of patients I've seen described as circus-sized. And also somebody who said that they were putting their patient on some phytoestrogens, and it said that they were taking phytoestrogens, which are presumably dog vitamins.
Yes, well, I'm sure that's just because they weren't using our system, of course. But that's actually a very big problem. One of the best ways to get speech recognition to work is to assume that people are saying things that are commonly said. And of course, in medical examinations, those words are not necessarily the same as what might be found in the rest of society.
Indeed. Neil.
Hi, I'm Neil Barge. I work for a company called TAP Biosystems. I've been designing robots for laboratory automation for about 22 years. Prior to that, I studied engineering here in Cambridge.
So a robot designer. What's the most fancy robot you've built?
Ooh, that's difficult to say. Some of them took quite a long
You
time.
haven't built a coffee maker for home? You haven't got teas made or anything?
No, we tend to buy those. The projects that we work on, there's teams of perhaps 20 people, and the project might take 1 to 2 years. So it's quite an endeavour to get the systems working reliably.
I think if you worked in my lab, you'd definitely be your first priority would be a robot to make the tea. I'm sorry.
Mm-hmm.
Paul.
So I'm Paul Meacham, and I work for a company called Airbus Defence and Space. And specifically, I'm a systems engineer on the ExoMars rover project.
What's ExoMars?
So it's a mission to go to Mars in 2016 with an orbiter, and in 2018 with a rover, which is a 6-wheeled vehicle about 2 metres tall or so.
So what, Ford not good enough for you then?
No, they don't make rovers.
So that's our panel of guests. So those are the people who are going to be answering our questions this week. But what about the experiments? We always like to be hands-on. We always like to do something up close and experimental. And in our kitchen corner, Dave and Ginny, hello to both of you. What have you got lined up for us?
Hi, so we're not actually going to be able to build a robot right here today, unfortunately, but we are going to show you some sort of elements that go into building robots.
So we're going to be looking at how you can make a robot move. We're going to be looking at why it's difficult to make robots work in really low temperatures.
And we're going to show you a little bit about how your brain does something that the voice recognition software finds really difficult to do.
Ginny and Dave, thank you very much. Please welcome our panel of guests this evening. So Blaise, let's kick off with you. So tell us a bit about what you actually do to try and make computers understand what we say. Why is that so difficult?
Well, it's difficult because there's so many ways that we produce language. There's so many different accents, and there's so many ways of phrasing things. And more problematic, actually, people keep coming up with new ways. So when you think you've got everything sorted, then people start adding some slang that never got seen before. They rephrase what they were saying. And also they speak in ways which are not actually grammatical. So a lot of the time, people think that we're speaking in full sentences, but of course, we're just speaking in phrases or sections of words, and people have some way of understanding that, even if it doesn't really make sense.
Didn't the people of Birmingham become rather offended recently when it turned out that the speech software on the council's telephone system couldn't understand what they were saying?
Yes,
That's true. It's true, isn't it?
I believe that is true, actually.
But why should the system object to the population of Birmingham?
Well, it's not a personal thing.
Well, I should hope not.
I mean, of course, there are some engineers who might have personal vendettas against the population of Birmingham. But in this case, it's probably because the computer hasn't seen any examples of people speaking in that particular way. And that particular way is possibly so different from what it has seen that it found it difficult to understand. So I suppose what you need to understand is that the way these systems understand language is that they look at examples of what they've seen before, and they look at examples of how people have spoken in a database that they've seen. So they'll look through a whole collection of sounds. So for example, we have sounds like a, b, k, etc. And each of those sounds has a different representation of a sound wave. And so when you look at the sound wave and you do some analysis of it, each of these different sounds has a different sound wave that comes out. And effectively what's happening is the computer is trying to find the most likely sound wave, or the most likely sounds for a sound wave that it gets shown. And in the case of the people in your example, probably what happened was that the most likely sound waves, according to what it had seen from other people, was actually different to what the person was saying.
So it doesn't have a problem with scales of people going A at the end of each line then?
Well, so in principle it wouldn't, as long as it had seen examples of it. And I think that's actually true of humans as well.
This is actually a really good point for me to do the first little bit of my demonstration. So what the people from Liverpool sounded like to a computer, we can't really understand. But I've got an example of something that might give you an idea of what they would have sounded like to the computer. I just have to get back to the laptop. Okay, so I want you to listen to this. Who thinks they understood that? A few people, but not everyone. Did some of you just not understand that at all? Yep. We got quite a few people who didn't understand. So if you imagine you're a computer, that's someone from Liverpool, that's what they would have sounded like. But your brains are amazing and they can use experience and learn from it. So if I carry on playing this, please wave your arms in the air. Now, I'm going to play you the exact same thing I played you before again, but hopefully this time you should understand it. Please wave your arms in the air. Did everyone understand it the second time? So that's something called sine wave speech. It's just been put through a sort of scrambling program to make it sound weird. And to start with, your brain doesn't know what to do with it. It's never heard those kind of noises before. I think I found it sounded a bit kind of like bird song, but I wasn't really sure what was going on. But once you know that it's speech and you know what it should say, your brain can unscramble it and it can figure out what it's saying. And actually, now you've heard one example of sine wave speech, you should be able to hear almost anything said in sine wave speech. So I've got an example of me saying something different. If you understood that, can you do what it says? Thank you very much. So once you've had an example of sine wave speech to use, you can understand other sine wave speech. And that, I believe, is what you're trying to train your computers to do.
Exactly. So computers are exactly like that. The more examples they see of someone speaking, the better they are at understanding. And probably what happened in that particular case is that they hadn't seen enough examples of people from that area. And if they had done, then they would be able to learn.
There was one bit of medical transcription I saw, and the doctor had actually said into one of these speech interpretation things, I would partially halve the narcotics. And the computer translated it as, I would prescribe parties and halve the narcotics. So it must be quite difficult when you've got words which some people tend to link words together, others speak with their words very clearly separated. How can you get a computer to tell those things apart? Because the patterns must end up looking quite similar.
They do, but there's a process by which the computer can just try out the different alternatives, and it'll essentially try every possible alternative and just look at which one is the most likely. So in your case, what's happening actually is that the computer is splitting up its analysis into two parts. So there's one part which looks at the sound, but there's also another part which looks at the sequence of words. And some sequences of words are more likely than others. And in fact, that's one place where you can get a lot of context. So for example, if you type into Google or if you type into any search engine, you can just write a few words and then it'll predict another word for you. And the same happens on your phone if you use something like SwiftKey or Swipe. These are systems where you type in your phone a few words and then it predicts what the next one is to help you go more quickly.
I've seen a few accidents happen where that's concerned, though.
Yes,
Yeah.
So that's exactly the same kind of accident that can happen. So the speech recognizer will incorporate that And of course, that can go wrong, but for the most part, it actually helps. So one big thing I've been looking at is how you can actually incorporate a whole dialogues context and incorporate the fact that you know what the person's been talking about and actually use that as well as just the most recent words.
Oh, that's clever. So what you're saying is that by looking at the context, in other words, the conversation that a person has already had, then when it sees a new word, you're narrowing down your search for what the possible words might be based on analysing a bit about the conversation. That sounds a bit spooky, though. It sounds a bit like kind of the computer's eavesdropping on what you're saying.
Well, I think it's something that we all do. So when we're talking to someone, we know what we're talking about and what the subject is. And so if there are two possible interpretations, then we'll choose the one which makes the most sense in the context.
Has anyone got any questions for Blaise? We need some questions now on anything to do with electronic technology, speech recognition, your funniest word prediction moment. Anyone got any howlers that they've seen when they've texted something to somebody and something they didn't expect to come up? Yes, who's this gentleman here?
I'm Reese Edmonds from Comberton. What is the highest wavelength and the lowest wavelength the computer can transmit?
Can you just clarify what you mean by transmit? Do you mean as in sounds that the computer can make?
Yeah.
To be honest, I'm not really sure what the answer to that question is. I believe it's several kilohertz, so that's the frequency rather than the wavelength. But there's a range, and actually the computer can both record and transmit higher and lower frequencies than our ear can hear.
Yeah, I mean, your ear is sensitive to about 50 hertz, which is 50 cycles a second. That's the lowest sound-ish that you can hear, about 50. Some people down to 20. And it's as high as 20,000 hertz when you're very young. And most people in this room who are a bit older will stop hearing sounds above 15,000 hertz. And in fact, people know that young people can hear some of these sounds better than older people, and they're using them as a form of repellent for young people. And there is, in fact, a shop. Is it in Wales, Ginny? Do you remember this? Yeah, and they actually had a problem with youths loitering outside, so they installed this buzzing system that bleeps at about 18 to 20,000 hertz, and they can hear it, and it's enormously annoying. But the adults don't get deterred from going in and buying their paper because they can't hear it.
But then the teenagers got their own back because they started using it as their ringtone. Because then when their phone went off in class, the teacher couldn't hear it going off, but they knew it was. So they got their own back.
How's that for ingenuity? Next question. Who else has got a question?
Hello, I'm Mark from Cambridge. I was just wondering, what's the limiting factor at the moment on the sort of processing of speech? Is it our understanding of how speech works, or are we waiting for processor power to increase?
I'd say it's more of an understanding thing. So we already have quite a lot of processing power. So actually, I'd say there are two big things. One is collecting examples of people speaking, so that we call that data, a big data source. And a big reason for big companies being much better at speech recognition is because they have a lot more of this data. The actual processing power is not such a big problem at the moment. It's very easy for us to get a large collection of servers together, computers together, to do the processing. So there is quite a lot more to do on the understanding of how to build better speech recognizers. And even that's been developing quite dramatically in the last few years. In the last 10 years or so, these systems have become really a lot more usable.
I've been quite impressed, though, because I've rung up a number of industries that have automatic telephone answering systems. And whilst I find them infuriating, they do work really rather well. And they say, tell me in a few words what your call is about. And you might say, my broadband doesn't work. And then it says, are you calling me about your broadband? And you say, yes. And it's very tempting to be incredibly sarcastic, isn't it? And does it understand sarcasm? Does that wash? If you go, no, I'm not, will it nonetheless still put you through to the broadband person?
I think it probably depends on how the person's designed it, but in most cases not. So actually, this is another thing we've been looking at, is trying to get computers to learn, as well as the analysis of the words, the meanings of sentences. And a big thing for that is trying to work out whether you've done something right or wrong. And what we're doing is getting the computer to try out different strategies of what it might do. So for example, in your case, you might try out and say, I think you wanted broadband, and then see if the person did. And then get the computer to learn by itself what these things mean. And for that, it's very important to see if you did the right thing or if you did the wrong thing, because that can inform you about how you should change your strategy in future. And actually, a pretty good signal for that, for example, is whether people swear at the system. And generally, that means that you've done something wrong. But actually, to check if you've done something right is a lot more difficult, actually.
Do you remember that Microsoft paperclip that used to pop up. Do you remember that Microsoft paperclip? Who here found that bloody annoying?
Definitely.
I saw a gag someone had done once, and they were so fed up with it. They'd written this sort of thing saying, "I've decided to kill myself," and whatever, and then the paperclip pops up and said, "This looks like you're writing a suicide note. Would you like some help with that?" Are you able to do emotion?
It's not something that I've looked at. And in fact, generally people have started looking at this, but it's actually very difficult. And partly because it's very difficult even for humans to decide what their emotion is just from listening to someone. So if you get 2 or 3 people and all of them listen to the same segment of audio, some will say that the person is very angry, others will say they have no emotion, and others will say that they're happy. And actually the agreement amongst humans is very low, around 60%. So it makes it very difficult for computers then to learn. And of course their agreement is even lower.
Any other questions coming in so far? There's one gentleman at the back.
Good evening, I'm Carlo for Cambridge. I would like to know whether there is any language which is easier to be understood to computers, or they are more or less all the same.
Yeah, that's an interesting question. So there is a difference in the ease of understanding. In some respects, English is actually the easiest of all. That's partly because we have a lot of what I call data, a lot of examples, because most of the internet is in English. The other languages which are more difficult for various reasons. So one is Chinese, and that's more difficult in some ways because of 2 reasons. One is that there's tonal variations in the understanding of the language. There are examples, for example, of words which to me or you might sound the same, but one might mean horse and the other mother. And if you say the wrong one, you can get into deep trouble.
In some supermarkets, horse and beef ends up being confused, doesn't it?
That's true, but I believe that's not because of the change in tone. So that's one interesting reason for the difficulty. Another, in the case of Chinese, is because the writing doesn't actually really segment words in the same way that we do with English. So there's a different idea of the meaning of a word. The other languages which are difficult for other reasons, so one is Turkish, and that's because of the way the words are structured. So in English we have prefixes and suffixes, and that's quite easy to deal with. But in other languages you get what are called infixes, so the words can change because of a change in the middle of the word. That makes things a lot more difficult for various technical reasons, because you get this huge explosion in the number of words that are possible.
Presumably the system can learn, though. Can it not teach itself and slowly get better?
Yes, so that's what we do in all of these cases with Chinese, Turkish, Arabic, etc. All of them have the best systems now being a system that's been learnt automatically. But it becomes more difficult when you have a very large explosion in the number of words, or when you start having to add extra things that affect the meaning.
It's obvious that if you want to make someone understand, you just speak loudly and clearly in English, don't you? Any other questions?
Hi, this is Fergal from Cambridge. I'm wondering how the speech recognition works in general. Is it more by pattern matching, or does it break all sounds down into the basic elements, wavelength, frequency, amplitude, and what other similar parameters make for different sounds and different accents and tones?
So what happens is it takes the sound wave and then it breaks it up into a sequence of what we call features. So these are a bit like what you call amplitude and so on. So they're slightly different, but effectively the idea is the same. And then what it does is it tries to find a sequence of sounds, which we call phones. So these are what are things like a, b, etc. So there's a collection which pretty much define all the sounds that we can produce as humans, a subset of which is used in English. And then it tries to find the most likely sequence of these phones, given the example of speech that it's been given. And the way it decides if something's likely is it looks at the distribution or the patterns that you would usually get for that sound of these features, so things like the amplitude. The specific ones which are typically used are a little bit more complicated. They're called null-frequency Kepstrel coefficients, which is
Say that again?
So null-frequency Kepstrel coefficients, also perceptual linear prediction coefficients.
How does that go down at parties?
It usually kills off all conversation, to be honest, which is why I usually try to leave it for as long as possible before bringing that in.
Any other questions?
Hi, Jenny from Cambridge. I was just wondering if the video phones were developed more, would that help, especially with emotion? So would you be able to match image with sound and you'd be able to tell by someone's face their emotion more?
Yes. So video gives a lot of help for emotion detection. It actually helps with a few other things as well. So you wouldn't think it's a problem, but actually one of the most difficult things to decide is when a computer should talk and when it thinks you're talking. Because if there's noise in the environment, then it's very difficult to know when the person stopped talking and when they're carrying on talking. And people pause, and it's never quite clear whether the computer should start talking now or not. And even people struggle with this because people, will interject and fight about who's talking. So if you have a video, it's much easier because you can actually, as well as listening to the audio, you can look at their lips and see whether they're still planning to speak. You can look at their face, and that gives some indication also of whether they're planning to speak. So video does help for more things than just the emotion. It also helps for other things, for what we call turn taking.
Can you also use facial expression to work out what someone might be trying to say? Because there's this famous McGurk effect, isn't there, Ginny, where actually if you show someone mouthing a word one way but play them a different sound, the person who's listening can get confused and hear a very different thing.
Yeah, exactly. We very much use the shapes being made by the face to help us work out what someone's saying, particularly in noisy environments. So if you see someone going, bah, making the kind of face they'd make when they make a ba sound, and you hear something that's a bit kind of, it could be a ba, it could be a ma, you'd assume that it's a ba because of what you can see them doing. So we definitely use that. So I would have thought that would be helpful for the computer as well, at least for some of those sounds.
Probably, yeah.
I'll have to work on that one. Ladies and gentlemen, Blaise Thompson from Vocal IQ. You're listening to The Naked Scientists with Chris Smith and with Ginny Smith and Dave Ansell, and our guest panel at the Cambridge Science Centre this month, where we're discussing robotics, are Blaise Thompson from Vocal IQ, Neil Barge from Tap Bio, and also Paul Meacham, who's from Airbus, formerly known as Astrium. We'll be hearing from him in a little bit when he'll be telling us how they're designing robots to explore Mars. But Neil, you make robots to work in the laboratory. So tell us about them. What do you actually do?
Our systems do all kinds of different processes in laboratories. We've been making systems for about 20 years, doing processing bottles or flasks like these. These are called tea flasks. They hold about 600 millilitres of liquid. It's about a pint. And
do you put beer in them then? Is that what you're doing?
We've had ideas of such things.
Do fermentation?
We do, yes, we do. And these are used to grow cells in all kinds of cells, animal cells, maybe insect cells. And the reason that that's done is to help with pharmaceutical research. Now, all around the world, there are thousands of biologists, and part of their job is to look after their cells. So once every few days, they'll need to get their collection of these flasks, take them out of an incubator, unscrew the caps, empty the contents of the liquid in there, basically give their cells some more food. The cells grow in the flask, and eventually the cells run out of space. So then you have to take the cells out of the flask, put them into a new flask to give them some more space to grow, keep them happy. Now, the cells grow at a certain rate, and sometimes they need to be fed and watered at the weekend, so people have to then work the weekend to keep looking after their cells.
That's what graduate students are for, isn't it?
It is, exactly. And but once people mature and get older, they don't like spending their weekends going into the lab to do these jobs. And that's where some of our systems come in, that our systems can automate the whole process so that scientists can actually use their time more valuably rather than doing the jobs of unscrewing caps and pouring and pipetting liquids.
Isn't it true, though, that the volumes of liquids that we're testing in laboratories for many of the modern tests, like DNA tests and things, are really, really small, and we're doing many, many hundreds of test tubes all in a row all at once, and humans are not terribly good at remembering where they got to, and you might make a mistake on the 89th tube and was it the 88th or the 89th? I better start again. And isn't a robot better at that?
Very much so. Many years ago, people used to do all of their work in test tubes, and as time progressed, we ended up with things like this. This is a plate with 1,536 wells in it, and each well is about 1 millimetre square and about 5 millimetres deep. And to access that, you need some small pipette tips. So in this box, there are 384 pipette tips. So we make systems that can pipette 384 samples at a time from plates like this into other plates like that for performing experiments en masse.
Any questions so far about how we can build robots to speed up research in the laboratory?
Well, I've got one on the email from Steve Lamble who says, why is this technology not used in Amazon warehouses? This was something that was big in the news recently, that we're still asking humans to run around with trolleys to pick things up. Sounds like the kind of thing, I mean, on a bigger scale, but similar to what you're talking about.
Yes, and actually I'm surprised that they wouldn't use automated systems in the Amazon warehouse, because many warehousing systems are automated. We made a system for the UK Biobank, which is for storage of biological samples. They're stored at minus 80 degrees. There's potentially millions of samples. The robot's actually working at about minus 20 degrees, but that's an example of an automated warehousing system.
So unlike the employees at Amazon who were complaining last year about conditions, robots don't complain. I suppose that's one big bonus, isn't it?
Indeed, they can work 24 hours a day, 7 days a week. Without stopping. They need some maintenance, but yeah, it's one of the benefits of automation is that they can work around the clock.
Is part of the reason why that's going to be very difficult because there's lots of different objects in the warehouse, and you're saying that robots are not that good at dealing with new and unexpected situations?
It's certainly a significant factor. Whenever we are looking at a new application, we try and standardize the things that need to be handled and handled as few different components as possible, and even try and design the things that we need to handle to make them suitable for robotic application. So I think you're right, the size and shapes of the packages will be a big factor, and if they were to try and automate it, they'd probably need to standardize on a small sort of set of different size boxes.
So do people come to you and say, this is our laboratory, we want you to design a robot that will do things in our laboratory, or do you make systems and then people buy them and design their lab around your system?
It's a bit of both. Quite often we're looking to develop new systems, so we talk to people and say, what is it that you do in your working life, and where are the real problems? Where do you spend all of your time? And so having those discussions, we identify that people spend a lot of their time doing fairly mundane tasks, and we think, well, if we can help with that task, is that worthwhile? And in some of the applications like the automation of cell culture, there's a variety of benefits. So it's not just about, say, a labour-saving action. When humans perform an operation, there's always some variability from one person to the next person, or what happens on Friday afternoon is often different to what happens on Monday morning. As a robot will perform the same task pretty much identically every time it performs it. So then you get more consistency of how the cells are actually growing in the flask. Robots also don't introduce contamination, so that's quite a problem when you're trying to do cell culture, making sure everything stays sterile. There's bacteria everywhere. It's very easy to contaminate samples, but robots aren't inherently contaminating.
Can't your robots catch computer viruses?
We try to avoid that.
What sort of software do they run on then? How do you program them?
There's a variety of different software packages at different levels. So usually there's a system PC that's running Windows.
Oh no.
Yeah. And that then would talk to, say, the arm that's got its own controller in, that's sort of coordinating the manipulation of each of its joints to move the pieces around.
What about actually making those movements though? Because I have a hand, and the most powerful feature of my hand is the fact that I can make my thumb meet the ends of each of my digits. Is that something that's very easy to replicate?
Not at all. I think generally, as humans, we underestimate how amazingly sophisticated our bodies are. So when you grab something with your hand, you've got an amazing sense of touch in all of your fingers, and that feedback with your eyes means that you can look at an object and pick it up, and you don't even think about it. Whereas with a robotic system, and a robotic system that doesn't have a lot of sensory feedback, we might not know that if we picked up a bottle and it had a missing cap, we might not know that. And then we try to process that and things would go wrong. So we do have to have a certain amount of sensors on the system, but relatively most robot grippers are pretty clumsy compared to our hands.
Any questions first before we've just got one question here.
My name's Jack and I'm from Comberton. How much would it cost to make and design one of these robots?
It depends on the sophistication of the system, but usually it's millions of pounds of development effort.
How much pocket money do you get? It depends on how many chores he does. You need a robot for that.
Hi, my name's Bea and I'm from Cambridge. I was wondering, to what level can these systems be used for pattern recognition within the lab environment? So currently, as you explained, they're doing some mechanical tasks, but when it gets to sort of, say, analyzing 900 different samples, they might provide a sort of speed of processing that is much quicker and help narrow down the amount of samples that, say, people working in the lab would have to, take further.
Yes, so I think that's probably more related to, say, a vision system and analysis of, say, a photograph. So as an example, it might be trying to recognize cancerous cells from non-cancerous cells, and that might be a very good application for helping that kind of activity in a lab. There are quite a lot of robotic systems that do have integrated vision systems on them. So an example would be in PCB construction, printed circuit boards inside phones. There are circuit boards with tiny components on, and in the assembly of those components are presented to the robot. The robot picks them up with a little tiny suction cup. It'll move it to a camera. The camera looks at it, decides where exactly it is, and sets the orientation of it for them to be able to accurately place it onto the PCB.
I've got a question here from Dominic in Cambridge. He says, why have robots been in use in factory production lines for so many years, but seem to have been very slow to appear in people's homes? Where's our robot to do the chores?
Yes, if only we had those robots in the homes. I think a lot to do with the economics of it. So in industrial processes where there's the same task to be done over and over and over again. So if you think about car production lines, where if you're making one car a minute, then having a robot that can do the same spot welds all the time is a very efficient way of applying a robot to a process because it's the same process. Whereas in a house, the household chores of washing up and doing the hoovering, dusting the cobwebs, they're very varied, and everybody's houses are, very different. So in terms of robots, there are vacuums that will sort of bump around, hoovering the carpet. What does it do on the stairs?
They defeated the Daleks famously, didn't they, the stairs? I tell you what we do want. We want an ironing robot. That's what we want, a robot that do ironing.
No, but then there's other solutions. It would be much better to have clothes that don't need ironing. So that would be, say, an engineer's approach to solving the problem.
Have you and Blaze got together to see if his speech recognition could be plumbed into your robot so that you could actually end up with a robot that would do as you told it?
No, we haven't, but it would be very useful because sometimes in developing systems, you can see something bad is going to occur. And if only you could shout, "Stop now."
Can you list one such example?
Yeah, well, these flasks, they're quite brittle material, and sometimes in developing the systems, you leave a flask in a place where it shouldn't be. The system knows where everything is, but if you open an incubator door and you decide to start moving flasks from one, you take a flask out, have a look at it, and that's very interesting, and put it back. If the system doesn't know that, it can quite easily just smash one of these flasks completely inside another flask. So basically got one flask right inside another.
Whoops, especially if there's Ebola in there or something. That could get
indeed.
nasty, couldn't it, Ginny?
So we've been talking about quite sort of complicated high-level robots there, but Dave's got a little experiment to show us the sort of very basics of how you get a robot to move.
Most robots are electrical and they've got a computer driving them, so you need some way of turning electricity into movement. So this is all based on a really basic effect. What I've got here is a coil of wire around basically a bolt, and I'm going to attach that to a battery, and that's over the top of some paper clips. And if I attach that to the battery...
Oh, the paper clips all jumped up and touched the bolt. So that bolt isn't a magnet in itself. They weren't attracted to it before you touched it to the battery.
That's right. But when you put electricity through a coil of wire, it turns into a magnet. And electricity and magnets are very, very well interconnected. So we can build an incredibly simple motor using these kind of principles.
So we've just made some paper clips jump, which is great. We've got some movement, but it's not really very useful. So you're going to do something now where we can get some slightly more useful movement.
So this is a model of basically the first electric motor which was ever built. It was built by Faraday. He used a bath of mercury, which we're not really allowed to, but luckily things have got easier since because magnets have got a lot stronger.
So you've got a sort of cylinder-shaped magnet, which you've attached to a base of a clamp, the base of a clamp, and then you're sitting a battery on the top of it. So you've basically built a tower so far.
Yeah, I'm just going to add a little bit more to that tower. The second magnet on the top with a little nut on the end of that, like a nut and bolt, because that gives me a little hole. And so what I want to do is complete the circuit. So at the moment, basically just a battery sitting there. And if I put a piece of wire between the top of the battery and the magnet at the bottom.
So that's a beautiful spiraled piece of wire. It looks a little bit like a Christmas decoration. You've sort of put it so that it's wrapping round the battery with one end sitting on the top in the nut. Oh, and it's started to spin. Can everyone see that? Brilliant. So what... So what's going on here then? Why is it spinning?
So if you have an electric current moving near a magnet, it actually gets a force on it. And if this is arranged so the electric current is going at right angles to the magnetic field, just at the bottom where it's right near the magnet, and that produces a force which pushes a little spiral round and round and round, and you get an incredibly inefficient motor. Luckily, engineers are better at this than I am, and they've spent 100 years or so getting far, far better designs of motor, which means that using this amount of power, you can actually do something useful rather than just make a little tiny spiral go round and round. But it's all based on similar effects with magnetic fields applying forces to wires with electric current running through them, and you can make things go round and drive your robots.
So will that just keep going now?
Until the battery goes flat or the wire bends, which it does occasionally. It does get quite warm after a while, which means I should probably stop it before it gets too hot.
Dave Ansell and Ginny Smith, thank you very much. And before them, Neil Barge from Tap Bio in Cambridge. You're listening to a special edition of The Naked Scientists, recorded here at the Cambridge Science Centre with me, Chris Smith, and also with Ginny Smith and Dave Ansell. We're talking robotics, and our guests are Blaise Thompson. He's from Vocal IQ, which is a local startup which are specialising in speech recognition technology. Also Neil Barge, who's from Tap Bio outside Cambridge. They make robots for laboratories. And Paul Meacham, who we're going to chat with now, is from Airbus, which was formerly known as Astrium. And you have the amazing party conversation, a starter, of being able to say that you make rovers for faraway planets.
Yes, although it tends to be the social equivalent of Marmite, I tend to find. Either it starts conversation or kills it dead. So we have a six-wheel vehicle, which we refer to as a Mars rover, that's going to Mars in 2018. The goal of the mission is to look for signs of life outside our planet. So whereas previous rovers, and they've primarily been American, this is the first European one, have looked for the conditions for life and things like that. We are looking for life directly.
And what are the hallmarks of life that you'll be looking for?
Well, it's a little bit difficult to say because when you try and characterize life, you find it's actually very, very hard. So essentially we have an organic molecule detector that looks for very simple molecular structures. And we also have a drill on the front of the rover that allows us to take samples from 2 meters below the surface.
Black & Decker.
It's actually more akin to an oil rig, actually, in the way it works. It has a single drill piece and extension rods that rotate into place to make a drill that is 2 meters long. And then the drill piece has like a camera shutter in the bottom of it that can push the sample in and bring it back up to be analysed by the organic molecule analyzer.
How big is this rover?
So it's sort of a medium-sized Mars rover, if there's such a thing. It's about 2 meters tall from the base of the wheels to the top of the mast, and about 1.6 meters long. So it's a reasonably sizable beast, and that means it can travel over most of the terrain we expect it to encounter.
There seems to be a sort of vogue for describing your rover in relation to a vehicle here on Earth. Curiosity famously dubbed the size of a Mini Cooper. So how big is your one then? How big is it?
Well, we're not quite that big. I guess we're sort of the size of
Reliant Robin.
I was thinking more like one of those, those big lawnmowers that you sit around and drive around on. It's kind of that sort of size, I think.
So how far down the development process are you with this?
Well, we've got to the point where we have several development models to test out the bits of the technology the rover will use that is less mature, simply because it hasn't been done before. And in particular, the autonomy the rover has, the ability the rover has to drive itself across the surface of Mars. We have several prototype rovers that allow us to demonstrate that and practice it and see what works, see what doesn't. But we're actually some way from building the flight rover.
And you can recreate Mars to test it on, can you?
We can, yes. So we have a big Mars yard, a giant sandpit, if you like, in Stevenage. And the rover essentially practices in there. It drives over rocks, it sees how it handles slopes. And our prototypes are deliberately developed such that they are the same weight on Earth as the real one is on Mars. So they behave in the same way as the real one will do when it gets to Mars, where the gravity is much lower. And therefore we can write all our clever software to control it, knowing it'll work on the flight rover when we get there.
Is the temperature on Mars at night time not close to minus 100, though?
It can be slightly lower than that, yes. I mean, daytime temperatures are around 0 to 10 degrees, which electronics typically like, but nighttime temperatures, as you say, can drop to minus 130, and they drop off very quickly because the Martian atmosphere is very thin and it just doesn't have the same heat retention capability that the Earth does.
But is it not quite good to have cold temperatures for electronics, because doesn't the electrical resistance drop when it's nice and cold?
It can do, but the real problem is that essentially when you get to the sort of below minus 100, you're starting to see your circuit boards is freezing, solder's going to start to break, even the circuit board will break in two, and so that means that it's now dead and you've got no way of repairing it. So we have to avoid low temperatures as much as possible.
So we have a little demo now to show you exactly what happens to various bits of electronics at very low temperatures.
So what I have here is an exceedingly jury-rigged circuit. I have some batteries, a little light, and a very long coil of wire. And in this thermos flask, I have some liquid nitrogen, which is sitting a little bit colder than Mars at about minus 196 degrees centigrade.
So you can see we've just poured some out into a cup, and you can see that it's bubbling, and that's because it's actually boiling. In the same way that your kettle gets lots of bubbles in it when it boils, when it comes up to 100 degrees, this liquid nitrogen will boil at room temperature, and all that vapour coming off is that kind of vapour as it's boiling. So we've got a nice little circuit here. It's a little bit makeshift. We've got some wire and we've got a bright red LED, which everyone can see is glowing beautifully. So what are you going to do with that LED?
So the first thing I'm going to do is cool down the wire.
So you're popping the wire into the thermos flask full of liquid nitrogen. We've got beautiful vapour going everywhere and it's making quite a noise. And now it seems to have quietened down. So what does that mean?
So now the wire is sitting about minus 200 degrees centigrade, and the wire actually is perfectly fine at this sort of temperature. And if anything, the LED will have got a little bit brighter because the resistance of copper drops an awful lot when you get down to this sort of temperature, I think even by a factor of 10. But if instead of that we cool down the LED, which is a piece of electronics, it doesn't work quite so well.
Oh, that looks so pretty. It's glowing in the cup of liquid nitrogen, and oh, it's gone off. It stopped working. Have you just broken it?
If I take it out again and let it warm up slowly, it comes back on.
Oh yeah, so it's back. It's not quite as bright as it was at the beginning, but it's getting there. Yeah, I'd say it's just as bright. So it wasn't that you'd broken it. It's just while it's that cold, it can't work. Why is that?
So LED and most of the clever bits of electronics are made out of materials called semiconductors. And these can conduct or insulate, and they can have all sorts of interesting properties. But in order to work, they need a bit of heat to kind of give the electrons a bit of a kick and let them move around. But as you cool them down, the electrons kind of gets locked up and can't flow with an electric current. And they basically just stop working. So if you get a piece of electronics cold enough, it just doesn't work.
So something to avoid on Mars, I guess.
Yeah, definitely, yes. So we have to manufacture the environment that the electronics sit in to be much closer to where the electronics do like to operate. So somewhere between minus 40 and 10 degrees centigrade. And the way we do that is we put all the electronics in a central core structure, which we refer to as the bathtub. And the bathtub essentially has the space equivalent of double glazing. So it has an inner skin and then a cold gas trap between that layer and the outer skin. And just like double glazing, it stops the heat from escaping and creates a thermal barrier. So you can control the temperature of the inside of that bathtub to whatever you like, typically somewhere between minus 40 and 10 degrees.
Where does the power come from?
Well, all our power comes from the solar panels that sit on top of the bathtub and essentially seal it. That's our primary power source when we're on Mars. We have a battery as well that charges up in the day to keep the rover alive at night. But in essence, yes, we are completely environmentally friendly and solar powered.
And these solar panels, how long will they keep the rover running for?
It's an interesting question because one of the big issues with using solar panels on Mars is they eventually get covered in dust, and it's very, very difficult to get that dust off once it's landed on the solar panel. And essentially, your efficiency, the amount of power you're generating from that solar panel drops off over the mission.
You need a robot to clean them.
Well, almost, but then that can get a little bit difficult because you end up scratching the glass because the solar panel is covered in glass, and then you have permanent damage, and then you will never generate enough power again. So it is a problem, and we oversize the solar panel to compensate for a bit of that. But fortunately, dust storms, which can envelop the whole planet on Mars, are seasonal. They tend to happen from the autumn equinox round to the spring equinox, and so it makes sense that our mission lands at the spring equinox, just after the dust storm season has finished, and then our nominal mission should be completed by the time it starts again.
Questions from the audience. Who would like to ask about building a robot to explore another planet?
Hi, it's Mark from Cambridge. I was just wondering, given that what can go wrong will go wrong, and that Mars is a long way away, do you tend to over-engineer the systems to try and ensure that they don't break, or does the rover have some ability of repairing itself at all?
Certainly, we do over-engineer it a little bit to guarantee that it's going to work over its nominal mission. But in fact, the main way we avoid problems is to carry two of everything. We have a prime and redundant equivalent of every single unit on the rover. So we have two computers, two power distribution units, two sets of sensors, and so on and so on. So essentially, if one breaks, you switch on to the B side, if you like, and use that instead, and they both work in exactly the same way.
Have you got any spare tyres?
Well, actually, we don't use tyres because they are made of rubber, and we can't take organics to Mars if we're looking for life. So we actually make the wheels of the rover out of metal, and they are sort of like a spring in a wheel. They compress slightly to allow us to climb over rocks and grip properly.
How do you actually control and steer the rover around on Mars?
Well, because Mars is so far away, and in the worst case, there's a 20-minute time delay, it's not practical to drive the rover by remote control. Even though it's monitored back on Earth, we actually want the rover to make as much of the decisions as it possibly can. And in fact, our rover is capable of accepting a target, which can be several hundred meters away and is simply a XY coordinate. And then the rover does everything else itself. It will use its cameras to image the terrain in front of it, identify where the rocks and the slopes are, figure out if certain areas of that terrain are safe or not, plan a path through it, and then drive that path all by itself. And in fact, we'll only see the rover once or twice a day.
I'm still disappointed that you can't sit in your lab with a radio control device and sort of think, I'm steering this thing. How far away is it to Mars? How far is your message having to go to get to Mars?
It varies. So the closest approach is 36 million miles. The furthest is 250 million miles. So and that's where the 20-minute time delay comes from, even travelling at the speed of light.
So 20 minutes for my message to go what I want it to do to get to
Yes,
the rover.
that's right. So if the rover was driving forward and you saw an obstacle you wanted to avoid, you press stop. And then 20 minutes later, it would have hit whatever the obstacle was you were trying to avoid because the signal took so long to get there.
Any other questions so far? There's one just at the back, this lady here.
Hello, I'm Sophia from Cambridge. I would like to know if this robot stays in Mars or do you bring it back?
Sadly, no. It's staying on Mars forever. The reason for this is quite simple. When you want to take lots of scientific instruments and you want to essentially have as big a rover as you can possibly send, and if you want to bring something back, you have to take the fuel with you to then launch it back off the surface of Mars and back to Earth. And of course, that severely limits the size of the rover, the number of scientific instruments and so on that you can send. So it's a simple choice, essentially. Do you want to do lots of science or do you want to get the sample back? And to this point, all the rovers have been on a one-way trip. But the mission that follows ExoMars is called Mars Sample Return, and it's a much simpler spacecraft just designed to land, take some samples, and then get back up and back to Earth. But the groundwork has been done by the rovers because they've figured out by travelling large distances where is interesting and where is not to take samples from.
What about making sure we don't bring back something horrible to Earth from Mars? What steps are in place to make sure we don't ruin our planet?
It's a big issue. I mean, it applies in both directions, actually. We have something called planetary protection. That means we can't contaminate Mars. But yes, if we're going to bring a sample back, it can't contaminate the Earth. So it's likely that the sample container would be essentially launched and then collected in orbit by another spacecraft that has not been down to the surface of Mars. That would then return it back to Earth, and it would be sealed in an entry vehicle to get it back down to the surface. So no part of a spacecraft that's been exposed to the Mars environment has actually been exposed then to Earth.
So that way there's no way it can deposit anything into Earth's atmosphere.
That's right, and you'd have about 10 minutes or so on landing to go and find it, collect it, and get it back into a clean environment.
What, before someone else nicks it? Or...
Well, hopefully not, because of the risk of contamination still. So.
Any other questions? Yes, Neil, go ahead.
What is the lifetime of a rover on Mars?
Well, the nominal mission, if I can call it that, is 218 days, or sols as they are on Mars, and that's reasonably typical. The Spirit and Opportunity rovers had a lifetime of 180 sols, and Curiosity is about 2 years. So that's when it has to achieve all its basic science goals. But of course the mission can go on and will go on beyond that, partly as a result of the over-engineering, but partly because we'll just keep running it until something breaks.
Ginny.
Steve on Facebook wants to know, we've got driverless trains, and you were talking about a sort of driverless rover. So when are we going to have driverless cars? And would we really trust them? Can we be sure that they'd actually be safe?
That's an interesting question. I mean, we are starting to make steps to that. I mean, Google have a car that can do some degree of driving by itself. It's probably only ever going to work if all the cars are driverless, because then there's less unpredictability, certainly. But I mean, certain features of it are appearing in cars these days, like lane control. So if you start to go outside of your lane, it will vibrate to let you know that's happening. So some features will come into our cars, but I think we're some way from all of us driving cars that are autonomous.
Any other questions from you guys out there? One at the back, just over here.
So this is Rhys Edmonds from Comberton. How long roughly will a rover be out on the surface of Mars per day?
Well, certainly at night we don't go anywhere. The rover is parked up at night because of the temperature drop, just to keep the rover alive. But in the day, it rather depends on whether we're at the science site or not. So we might be drilling holes, we might be doing analysis, that sort of thing. But if it's a driving day, we expect to travel about 70 metres, and that's all being done autonomously. And over that 218 days, we'll be doing about 4 kilometres or so. So obviously we're not driving every day, but that's typically what we have to design for.
When will this actually blast off heading for Mars?
We're due for launch in 2018, and the launch date is quite specific because you can't just go to Mars whenever you like. We have to wait for the planets to be in the correct alignment relative to each other, such that by the time you blast off and get to Mars orbit, Mars is there. So that only happens every 2 and a bit years, and that's why the first part of the mission goes in 2016 and the rover goes in 2018, because they have to wait for the next opportunity.
Now, Curiosity came down in this incredible way where they actually had a platform that had thrusters that stopped the rover above the surface and then winched it down onto the surface of Mars. I mean, it was incredibly elegant. How are you going to land? Not like Beagle, hopefully.
No, hopefully not. But we'll also be using powered descent, because that's really the standard for rovers of this size. Partly because you want to have a nice gentle landing, but partly because you want to target the rover very, very carefully. Now we have a reasonable idea of where we want to take samples. The rover has to be able to be directed to that place, and it can't just bounce around for miles. So we essentially have a landing platform that has rocket motors in it, but the difference is we're sat on top of it, not being winched down from it. And we land the whole thing, because the difference between us and the Curiosity mission is that we have instruments and so on the actual landing platform. So we want to land them both in the same place so we get consistent data.
I'm Kate from Cambridge. I've got a question. How would the Mars rover have done on Robot Wars? And does the panel think that more kids would get into robotics if the BBC brought it back? Or how else should kids get into robotics?
I don't think our rover would fare very well, because it's very, very slow. There are rather different constraints when you're 250 million miles away. So actually we would be severely outclassed, I think, on the Robot Wars arena. But yes, you're absolutely right. I mean, that sort of thing is a great inspiration for young people to go and explore, engineering, software. Something like a rover has so many different aspects of engineering that it's actually quite a good way to explore lots of different areas.
Neil, do you think one of your arms would do quite well? Would it be able to sort of punch people?
What, in Robot Wars?
In Robot Wars, yeah.
Yeah, quite possibly. I think it would do quite well. I always
Pipette the
Yeah.
opposition to death.
Yeah, when I was younger, I quite fancied entering the competition. Maybe I'm not too old.
Now, I've got a sort of more general question for all of you, I guess, is Maybelline at Mabel Bark on Twitter wants to know, could we power robots on something other than, well, I guess we use electricity, and could we use something like food to power robots?
Well, I can start by saying something which is quite important for planetary exploration of the future, particularly when we go so far away from, outside the orbit of Mars, where solar power is starting to become not a viable source. And it may even be applicable for a human mission, particularly with regards to getting something back without having to take lots of fuel with you to do that. And one of the ideas is that you would actually mine methane and use that as your fuel to power your rocket or whatever to get back to Earth.
It's really a fracking mission.
Oh, yes, yeah.
Is that what the drill's for?
Not in this case, but...
Any other questions from everyone at home?
So Joe asks, there's been this movie out recently, Her. I haven't seen it, but I think it's about someone falling in love with one of the sort of voice recognition systems. And we were wondering sort of how important is it to have an emotional connection to a robot? And sort of linked to that, what do you need to have that emotional connection? Do we need something that looks human, that sounds human?
Yeah, I think it's actually very important. People like using robots that have more emotion. And in some ways, that's possibly why people have been more interested in Siri, which is from Apple, than from Google's product, which is called Google Now. Because Siri has this kind of personality, and you can ask it if Siri will marry you, for example. And it'll
What does
come
she
back.
say?
I think usually she says no.
She's fussy then.
She's very fussy, and I think has refused most of the population. I think she likes her own company. So I think the things that we get affected by are things like the voice. It's quite easy for us to hear emotion in a voice, and that can have a very big impact. So I think the more that you have, the more affinity you can attach to the robot. But I think it's not necessary that you have everything. So you probably don't even need to have a face or a picture of a face. You can start developing some emotion for your robot/device, even if it doesn't have a picture of it.
Do you give your robots names, Neil?
Yes, we do for the projects. They all have the names, and they've had various themes of names over the years.
One of the diagnostic lab I work in, they've got things like Rod, Jane, and Freddie,
Yeah.
and stuff like that. I mean, Scooby Doo. I mean, everyone thinks it's quite funny, but it does actually kind of endear the staff to the machine they're using to do all these tests.
Yeah, and we've wasted many hours debating what we should call the systems, our robots.
And
the debates continue.
Have you got a nickname for your robot?
Yeah, all the prototypes have names. So we've got Bridget, Bradley, Bruno, and Brian are our four.
So you favour bees then? You
We
like
do,
bees?
yeah. So it started with Bridget because our prototypes are referred to as breadboards in it's the correct engineering term for them. So they often get shortened to BB in the documentation. And one of the members of the project team was a fan of Brigitte Bardot, and so it became known as Bridget, and we've sort of followed on with the bees from there.
That kind of leads on to, there's a question here from Jenny Lugo, who wants to know if there are any sort of ethical issues around the use of robots. And she quotes this article she read, which had the line, "We had people interact with very cute baby robotic dinosaurs, and then at the end of the workshop, we asked them to torture and kill them. They were pretty distressed by this."
I'm not
so
surprised.
Does naming your robots and sort of giving them a personality then mean you're going to be sad when they break, or are you going to miss your robot that doesn't come back from Mars?
Well, yeah, I guess so. There's a very sad cartoon that does its rounds on the internet of Spirit, asking whether it can come home or not. But I like it. Gives them a bit of a personality, and they do have personalities. And as I say, it probably makes us care for them, I think.
The Chinese lander that was exploring the moon across the Christmas period developed a problem, and it sent back a message, and it said, "My masters can't manage to shut me down in time for the cold weather that's coming, so I might not wake up again in the morning. Goodbye."
Yes.
and it got virally tweeted around the world because I think everyone felt very attached to this machine.
Mm-hmm.
Do people get attached to your lab machines?
I think attached is a strong word, but yeah, if you've been working on a system, on a robot for a year, and you know it's a prototype, and at some point it's going to go in the skip, then you put so much effort into making something, and then once it's served its purpose, to throw it away. That's sometimes tough.
Well, we must leave it there. It remains for me to say a very big thank you to our panellists, and I hope you'll join me in thanking Blaise Thompson from Vocal IQ, Neil Barge from Tap Bio in Cambridge, and also Paul Meacham from Airbus, and our kitchen scientists, Ginny Smith and Dave Ansell. Thank you very much. You have been listening to a very special edition of The Naked Scientists, which was recorded here at the Cambridge Science Centre. My name is Chris Smith. A very big thank you to Kate Lamble for doing the production and pulling this evening's show together. And please come and join us again at the same time in 2 months' time in April. Thank you.